Differential equations are one of the most powerful tools in all of science and engineering. Wherever we find systems that change, mechanical vibrations, electrical circuits, the flow of heat, the growth of populations, differential equations are there to describe them. In this video, we're going to build up from the fundamentals of calculus, derivatives, and integrals. We'll use those tools to understand what differential equations actually are, how to classify them, and how to solve them. Let's start with a classic example. This device here is a spring mass damper system. It has a mass sitting on a spring with a damper alongside it. When we disturb the mass, it oscillates. The equation that governs its motion is m times d squared x over dt squared plus c times dx over dt plus kx equals 0. Notice that every term involves a derivative, a rate of change. That is the hallmark of a differential equation. To understand it, we first need to understand derivatives. Before diving into the mathematics, let's build some intuition. When we push a spring beyond its elastic limit, the relationship between force and displacement stops being a straight line. It curves. It becomes nonlinear. The slope of that force-displacement curve is the stiffness. Notice how the stiffness, the slope, is different at every point along the curve. That's a rate of change. Similarly, velocity evolving over time follows a complex curve. A derivative is simply the slope of a curve at any given point, the instantaneous rate of change. Let's now see exactly how to compute that. Consider the simple function y equals x cubed. Its graph looks like this. To find the slope, the derivative at any point, we pick two nearby points on the curve. Point 1 is at x, giving y value x cubed. Point 2 is a small distance delta x away, giving y value x plus delta x cubed. The slope of the line connecting them is x plus delta x cubed minus x cubed divided by delta x. Expanding the numerator, we get 3x squared delta x plus 3x delta x squared plus delta x cubed, all divided by delta x. Simplifying, 3x squared plus 3x delta x plus delta x squared. Now here is the key insight. As we make delta x smaller and smaller, bringing the 2 points closer together, the extra terms vanish. In the limit as delta x approaches 0, the slope becomes simply 3x squared. That is the derivative of x cubed. Let's look at this graphically. The top panel is our function y equals x cubed, the sine curve. The bottom panel is its derivative, dy over dx equals 3x squared, the yellow parabola. Notice the relationship. Where the cubic function is at its flattest, around x equals 0, the derivative is at its minimum value of 0. At the edges, where the cubic rises or falls steeply, the derivative is large. The derivative tells us the slope of the original function at every single point. Dy over dx is read as the derivative of y with respect to x. The notation tells us we're looking at how y, the dependent variable, changes as x, the independent variable changes. From our calculation, we can spot a pattern. For f of x equals x cubed, the derivative is 3x squared. For f of x equals x to the n, the derivative is n times x to the n minus 1. This is the power rule. The exponent comes down in front as a multiplier, and the exponent itself decreases by 1. It's one of the most used rules in calculus. The derivative of x to the fifth is 5x to the fourth. The derivative of x squared is 2x, and the derivative of x to the 1 is just 1. Here is a table of the most common derivatives you'll use throughout engineering and physics. The derivative of any constant is 0. Constants don't change, so their rate of change is 0. For x, it's just a. The power rule gives us n, x to the n minus cosine of x. You can see this in the graphs on the left. Wherever sine of x is at a peak, cosine of x equals 0. Wherever sine of x is steepest, cosine of x is at its maximum. The cosine derivatives to negative sine, e to the x, is famous for being its own derivative. And the derivative of the natural logarithm is 1 over x. Memorize this table. You'll use it constantly. What if our function has multiple terms added together? The linearity rule tells us we can simply differentiate each term separately and add the results. For y equals x squared plus 3x, the derivative is 2x plus 3. This also means we can pull constants out. The derivative of 5 sine of x is just 5 cosine of x. Linearity makes differentiation a term-by-term operation. Now let's look at a more complex function. Y equals e to the negative 0.2x times sine of 3x squared plus 1. This function has 3 components layered inside each other. There's an exponential term, a sine term, and inside the sine there's a power term. To differentiate something like this, we need 2 more rules, the product rule and the chain rule. The chain rule handles composite functions, functions inside other functions. If y equals sine of u, where u is itself a function of x, say u equals x squared, the chain rule says, differentiate the outer function, evaluate it at u, then multiply by the derivative of the inner function. In symbols, v of u prime equals v prime of u times u prime. So for y equals sine of x squared, the outer function is sine, its derivative is cosine. The inner function is x squared, its derivative is 2x. Putting it together, dy over dx equals cosine of x squared times 2x. Here's a complete example combining all 3 rules. For y equals 0.1x times sine of x squared plus cosine of 0.3x squared plus 1/6. The first term needs the product rule. U is 0.1x, v is sine of x squared. By the product rule, u prime times v plus u times v prime. U prime is 0.1. V prime requires the chain rule on sine of x squared, cosine of x squared times 2x. So the first term's derivative is 0.1 times sine of x squared plus 0.1x times 2x times cosine of x squared. The second term only needs the chain rule, negative sine of 0.3x squared plus 1/6 times 0.6x. By linearity, we just add the 2 results. One of the most important applications of derivatives in engineering is finding stationary points, points where the function is neither increasing nor decreasing. These occur wherever the derivative equals 0, dy over dx equals 0. The top panel here shows a complex function with several peaks and troughs. The bottom panel shows its derivative. Wherever the yellow derivative curve crosses 0, the original function has a stationary point, a local maximum or minimum. This is how we optimize designs. Find where the derivative is 0, and you found the extremum. In structural engineering, material science, and thermodynamics, stationary points correspond to critical states of the system. So far, we've only considered functions of a single variable, x, and differentiation, with respect to that one variable. But what if a quantity depends on more than one variable? Consider this metal rod. The temperature at every point along its length, shown by the graph T of x, varies with position x. But temperature also varies with time. As you heat one end, the temperature distribution changes from second to second. Temperature is a function of both position x and time t, When a function depends on multiple variables, we use partial derivatives. Two famous partial differential equations both have this same mathematical structure. The heat equation, partial T over partial T, equals alpha times partial squared T over partial x squared, describes how temperature distributes itself in a material over time. Alpha is the thermal diffusivity. Fick's second law of diffusion, partial C over partial T, equals d times partial squared C over partial x squared, describes how a concentration of particles, gas molecules, solute, impurities spreads through space. D is the diffusion coefficient. Same equation form, completely different physical phenomena. This is one of the beautiful unifying powers of mathematics. Let's clarify what a partial derivative actually means. In the heat equation, the left side, partial T over partial T, is the partial derivative of temperature with respect to time. This tells us how temperature at a fixed location in space changes as time passes. We hold x constant and see how T evolves. The right side, partial squared T over partial x squared, is the second partial derivative with respect to position. This tells us the spatial curvature of the temperature profile at one instant. We hold T constant. To see how partial derivatives work, take y of x and t equals 3x squared t plus 2t squared. The partial derivative with respect to x, treating t as a constant, is 6xt. The partial derivative with respect to t, treating x as a constant, is 3x squared plus 4t. We write the curly partial symbol to indicate it's a partial derivative, not a total derivative. Now let's turn to integration, the reverse operation of differentiation. Here is an electric motor starting up. When it first activates, it draws a large spike of power, shown by this yellow curve. The y-axis is power in joules per second, the x-axis is time. This curve is dE of t over dt, the rate at which the motor consumes energy. But what we really want to know is the total energy consumed. To get from a rate of change, power, back to the accumulated quantity, energy, we integrate. Here are both curves together. The top panel shows E of t, the total energy accumulated over time. It grows continuously as the motor runs. The bottom panel shows dE of t over dt, the power, which spikes at startup and then decays. The relationship between them is simple. Differentiate E of t and you get the power curve. Integrate the power curve and you recover E of t. The green histogram bars show how integration works conceptually. The area of each small bar, power times a small time interval, is a small packet of energy. Sum all those bars as the width approaches zero, and you get the exact energy. That sum in the limit is the definite integral. Integration is the reverse of differentiation, and the power rule runs in reverse too. The integral of x to the n is x to the n plus 1 divided by n plus 1, plus a constant c. The plus c is essential. When we differentiate any constant, it vanishes. So when we integrate, we must acknowledge that there was possibly a constant in the original function. This is the indefinite integral. The table on the right shows the integrals of all our standard functions, the mirror image of our derivative table. For a definite integral, one with specific upper and lower limits, we evaluate the antiderivative at both limits and subtract. For the integral from 3.5 to 4.5 of x to the fourth dx, the antiderivative is 1/5 x to the fifth plus c. Evaluating at 4.5 minus evaluating at 3.5, 1/5 of 4.5 to the fifth minus 1/5 of 3.5 to the fifth equals 264.0. Geometrically, this is the shaded area under the curve y equals x to the fourth, between x equals 3.5 and x equals 4.5. The definite integral gives us areas, accumulated quantities, total changes. Sometimes a function is too complex to integrate directly from our table. For the integral of 2x times cosine of x squared dx, we use integration by substitution. Notice that 2x is the derivative of x squared. So if we let u equal x squared, then du equals 2x dx. The integral becomes the integral of cosine of u du, which is simply sine of u plus c. Substituting back, sine of x squared plus c. The key is recognizing the pattern. We need a function g of x inside another function f, and g prime of x sitting out in front as a factor. The formula is the integral of f of g of x times g prime of x dx equals the integral of f of u du. We now have the two fundamental tools of calculus in hand, derivatives and integrals. Let's see how they combine to form differential equations and why these equations are so central to engineering. We'll look at three classic physical systems. First, a cantilever beam. This steel beam is fixed at one end and loaded with a 100-kilogram weight at the free end. The beam bends. The shape of the deflected beam, how far it deflects at each point x along its length, is described by a differential equation. The curvature of the beam depends on the bending moment, which itself depends on position. Second, our spring mass damper system from the introduction. Three elements: the mass m, the spring with stiffness k, and the damper with damping coefficient c. When the mass is displaced from its equilibrium position, the spring pulls it back and the damper resists motion. The resulting oscillation and how it decays over time is governed by the differential equation we saw at the start. M times x double dot plus c times x dot plus kx equals 0. Third, an RLC electrical circuit. This circuit has a resistor R, an inductor L, and a capacitor C, all in series within a C voltage source, E of t. Applying Kirchhoff's voltage law, the sum of all voltage drops around the loop equals the source voltage, gives us L times the second derivative of charge Q with respect to time, plus R times dQ over dt, plus Q divided by C, equals E of t. The charge Q is the quantity we're solving for. Notice, this equation has the same mathematical form as the spring mass damper equation. Mass corresponds to inductance, damping to resistance, stiffness to 1 over capacitance. The mathematics is identical. Differential equations come in two major categories: linear and nonlinear. A linear differential equation is one where y and all its derivatives appear only to the first power, no y squared, no y times dy over dx. The equation dy over dx plus a y equals 0 is linear. Change y to y squared and it becomes nonlinear. The equation y times dy over dx plus a x equals b is also nonlinear because of the y multiplied by the derivative. Why does this matter? Linear equations have powerful, well-developed solution techniques. Nonlinear equations are generally much harder to solve, often requiring numerical methods. Most of this video focuses on linear equations. Let's classify our spring mass damper equation properly. It is second order, because the highest derivative is d squared x over dt squared. It is ordinary, because there is only one independent variable. Time t, there are no partial derivatives. It is linear, because x and its derivatives all appear to the first power only. It is homogeneous, because the right-hand side is 0, there is no external forcing. and it is autonomous because the coefficients m, c, and k do not explicitly depend on time. Knowing the classification tells us immediately which solution methods are available. Here's a nonlinear example for contrast. Sine of d squared y over dx squared plus y squared plus a x equals b. This is second order and ordinary. It's nonlinear because of two things: the sign of a derivative and the y squared term. And it's non-homogeneous because the right-hand side is b, not 0. This equation cannot be solved by the standard linear methods. It would typically need numerical techniques. There are several standard methods for solving ordinary differential equations. In this video, we'll cover 5 of them: direct integration, separation of variables, the integrating factor method, complementary and particular solutions, and the Laplace transform. Each method applies to a different class of equations. Let's work through them one by one. The simplest method is direct integration. It applies when the differential equation has the form: the nth derivative of y equals some function of x only, no y term on the right. We solve it by integrating both sides n times, collecting a constant of integration each time. Example: the Euler-Bernoulli beam theory gives us d squared y over dx squared equals the bending moment m of x divided by the flexural rigidity EI. For this cantilever beam with a point load P at the free end, the bending moment at position x is m of x equals negative px. So d squared y over dx squared equals negative px over EI. Integrating once, dy over dx equals 1 over EI times negative px squared over 2 plus a constant c1. Integrating again, y equals 1 over EI times negative px cubed over 6 plus c1 times x plus c2. We find c1 and c2 from boundary conditions. At the fixed end x equals 0, both the deflection y and the slope dy over dx are 0. Substituting, c1 equals 0, c2 equals 0, so y equals negative px cubed over 6ei. The maximum deflection at the free end, x equals L, is PL cubed over 3ei. The second method is separation of variables. It works when the right-hand side of dy over dx can be written as a function of x only times a function of y only. dy over dx equals f of x times g of y. We rearrange. 1 over g of y times dy equals f of x times dx. All the y terms are on the left, all the x terms are on the right. Then we integrate both sides independently. For dy over dx equals x squared times y, we separate to get 1 over y dy equals x squared dx. Integrating the left, the natural logarithm of the absolute value of y integrating the right, x cubed over 3 plus c. Exponentiating both sides, y equals a times e to the power x cubed over 3, where a equals e to the c is an arbitrary positive constant. We determine a from an initial condition. To put our work in context with the full scope of applied mathematics, let's look briefly at the Navier-Stokes equations, the governing equations of fluid dynamics. These 3 vector equations describe how the velocity field of a fluid evolves in space and time. They contain both partial derivatives with respect to position and time. On the left, the inertial terms, density ρ times the material acceleration of the fluid. On the right, the negative pressure gradient, the viscous stress terms involving second derivatives of velocity, and the body force terms like gravity. The Navier-Stokes equations are non-linear partial differential equations. General analytic solutions are unknown for 3 dimensions. In fact, Proving whether smooth solutions always exist is one of the 7 Millennium Prize problems. Most practical fluid simulations solve them numerically on supercomputers. Here is a nonlinear ODE in action, the logistic growth equation. dy over dt equals 2y times 1 minus y over 500. This describes a bacterial population, y growing over time. The term 2y captures exponential growth. The more bacteria present, the faster they reproduce. But the term 1 minus y over 500 introduces a carrying capacity of 500. As the population approaches 500, growth slows. Exactly at y equals 500, the growth rate is 0. The graph shows multiple solution curves, each starting at a different initial population and each converging to the carrying capacity. Notice the characteristic S-shape or sigmoid curve. Because this equation is nonlinear, it doesn't have a general closed-form solution obtainable by separation of variables in a simple way. We can use numerical methods, like Euler's method, to approximate solutions. Starting at the initial condition, 0, 1, we step forward with step size h equals 0.5. The next value is the current value, plus h times the rate of change at the current point. As our final application, consider a drone. To fly stably, a drone must control its pitch angle, the tilt of its nose up or down. The equation governing the pitch dynamics is d squared theta over dt squared equals tau y divided by iy. The second derivative of the pitch angle theta with respect to time, the angular acceleration, equals the torque tau y, applied by the drone's motors about the y-axis, divided by the moment of inertia iy, about that axis. This is a second-order, ordinary differential equation. To fly, we need to solve for how to choose tau y, how hard the motors push, to make theta track a desired target angle. To make the drone follow a target pitch angle, r of t, we use a PID controller. PID stands for proportional integral derivative. The controller computes the error, E of t, the difference between the target pitch angle r of t and the measured pitch angle y of t. The control signal u of t, which commands the motors, has 3 components. The proportional term, Kp times E of t, provides an immediate correction proportional to the current error. The larger the error, the harder the motors push. The integral term, Ki times the integral of E over time, eliminates steady-state error. If a small persistent error remains, the integral accumulates and drives it to 0. The derivative term, Kd times the derivative of E, provides anticipatory damping. It looks at how fast the error is changing and resists rapid changes. Together, these 3 terms, involving integration and differentiation, allow the drone to fly stably. All 3 are direct applications of the calculus operations we covered earlier in this video.